Welcome to Lab 4, Part 1, where we will cover the Newton-Raphson method. Here we have the definition of the method, and we will use the following procedure as follows, which starts by setting an initial guess x0, a tolerance of epsilon s, and a maximum number of iterations n. Then at iteration I, we will calculate x at I plus 1, which is approximately x of I minus f at xi divided by f prime at xi, and we will also calculate the error epsilon r. Then if epsilon r is less than or equal to epsilon s, or if I is greater than n, then we stop the procedure, otherwise we repeat. As always, we will start by importing pandas to display our tables. Then we will import SymPy, which we will use to do our calculations. Now we can go ahead and declare our function called Newton with the input f, the equation, x0, the initial guess, EPS, the stopping error, and nmax, the maximum number of iterations. Then a colon. First, we will find the first derivative of f, which we will use later in our calculations. We will set this equal to fp equal to f dot diff, and here f will be a SymPy expression. Then we will initialize our tables. The first is x table, which is initialized by x0, our initial guess. Then error table, which is initialized by 1, and I, which will start at 0. Now onto our while loop, which will keep looping while I is less than nmax, and while the absolute value of error table at I is greater than EPS. On every iteration of I, we will use this equation to calculate xi plus 1, and we will set the value of xi plus 1 equal to x new, and then the equation, which starts with xi, and this translates to x table at I, and then minus. Then we have the fraction, which has a numerator of f at xi. Since f is a SymPy equation, we must use the subs function to substitute a value into x. So f dot subs, round brackets, curly brackets. Now we will replace the symbol x in the equation f with the value xi, which is x table at I. Then we have f prime at xi. So we will use fp, which we have declared above. So fp dot subs, and once again substitute x with the value of x table at I. Now that we have the value of xi plus 1, we will append this to our x table. Going back to the procedure, we have calculated xi plus 1. Now we must calculate the error. So here the error ER will be equal to x table at I plus 1 minus x table at I, all divided by x table at I plus 1. Now append this error to our error table, then increment I by 1. Okay, now let's step outside our while loop, and here we will build our table T equal to panda.dataframe, and then a list comprehension. Now our first column will be I, our second column is x table, our third column will be our error table, and then our for clause, which is for I in range of the length of x table, and then the column headers, which will be iteration x, and then error. Now finally we can display our table T. So here we have the full code for our Newton-Raphson method. Next, we will go ahead and test our function. First, we must declare x as a symbol using sympy.symbols and then x. Once we have x, we will declare our equation with respect to x. Let's say our equation is g at x, and we will return the expression of sympy.sine of 5 times x plus sympy.cos of 2 times x. Since g is a function and we want a SymPy expression, we have to pass our symbol x as the input into g. So display g, and then the input is x. So this is the SymPy expression we pass in as f into our Newton function. Now let's go ahead and call Newton, pass in our SymPy expression, with an initial guess of 0.1, a stopping error of 0.005, and a maximum of 100 iterations. And here we have our table. On the very last column, we see after 4 iterations, we get an x value of negative 0.224 and an error of 0.000797. Now we will see how we can use SymPy's endsolve function to get the same solution. So as before, we must import SymPy as SP, then set our symbol x equals SymPy.symbols x. Once again, we will use the same function g as before, which is SymPy.sign of 5 times x plus SymPy.cos of 2 times x. Now we can call SymPy's endsolve function as follows: SymPy.endsolve, and the first input is a list of all of our equations, in this case g of x. The second input is a list of all the symbols used in our equations. In this case we only have x. And the third input is a list of all the initial guesses for each of our symbols in our second input. Here our initial guess for x is 0.1. Now let's go ahead and run this. The output is negative 0.2243, which is what we got before. One way to check our solution or to get an initial guess is to plot the function. So here we will use matplotlib to plot our function. And we will also use numpy to get a list of all our x values. And first let's set x values equal to numpy.arange from -1 to 1 with a step size of 0.1. Now we can plot g using plt.plot the x values, comma, the y values, which we will find using a list comprehension. So square brackets g at I for I in our x values list. Before we show the plot, we can also draw the grid and then finally plot.show. From the graph, you can see our solution, negative 0.224.